Good evening, everyone. My name is Tony McBride. I'm the Director of Advocacy at the IOP, and it's my very great pleasure to welcome you to Quantum Computing, Hope or Hype, jointly hosted by the Institute of Physics and the German Physical Society. Tonight, we explore one of the most exciting and, dare I say, one of the most hotly debated frontiers in science and innovation, quantum computing. Is it a visionary promise, or has its potential been overhyped? And if anyone was unsure whether this is an important topic, let me say that the fact that more than 800 of you registered for this event will tell you that it is. The event tonight forms part of a lecture series that began back in 2020 with a focus on climate change, and which started a fruitful tradition of collaboration between our organisations. And since then, we've tackled important and timely topics such as volatile energy, net zero, mobility systems, energy storage, robotics for medicine, and last year, nuclear fusion. I just want to let you know how proud we are of our international relationships, such as the one that we have with the DPG. And you will all know better than me the importance to the physics and the wider scientific communities of international collaboration to high quality research, to learning, to knowledge exchange and innovation. All of that being so, we believe very strongly that strong, active and long-term partnerships must be maintained if our communities are to remain at the forefront of scientific discovery and innovation, and to realise all of the wealth of societal, economic and political benefits of science and of science diplomacy. And that's why together our organisations recognise the importance of bringing together experts from the communities and the countries that we represent to share their perspectives, to discuss global challenges and the role that physics plays in meeting them. And it also gives us an opportunity to highlight how multidisciplinary approaches can benefit for society. This discussion comes at an absolutely pivotal moment. 2025 marks the International Year of Quantum Science and Technology, and for our part, the IOP has been leading celebrations across the UK and Ireland. During our recent Quantum Week, we showcased breakthroughs in quantum metrology, secure communications and computing, demonstrating how quantum technologies can transform healthcare, climate solutions, and industry. So it's both timely and exciting to be holding this event this evening. All that remains for me is to share my thanks with the speakers and to the organisers on behalf of the IOP, to say that I hope you all enjoy the event, and to introduce Karl, Executive for International Activities at our partner, the German Physical Society. Over to you, Karin.
Ich hampel hier gerade in der ganzen Konferenz rum. Ihr seid in meinem Bild. Ah, Mensch. Ich bin nämlich im Bild.
Nee, jetzt sind wir hier.
Jetzt seid ihr da, ne?
Ja.
Ich glaube, wir sind schon entmutet.
I do not know I'm starting or not. We had a little technical problem, but I will very short only to say a very warm welcome to all who joined us for this panel on behalf of the DPG. And I think we all are waiting for a very interesting discussion. And so I immediately would give the floor to our moderators, Anke Lohmann for the British side and Matthias Zimmerman for DPG. And I would ask you to introduce yourself. Thank you.
Thank you, Karin, and thank you, Tony, for the introduction to the panel. So I'm Anke Lohmann. I'm the chair of the Quantum Business Innovation Growth Group at the IOP. And Matthias?
Yes, so I'm Matthias Zimmerman. I'm a researcher and group leader at the German Aerospace Center at the Institute of Quantum Technologies.
Thank you. And with that, I would like to start the session. So framing the question again. Quantum computing has reached remarkable milestones from scalable hardware to improved quantum gate fidelities and high-level programming languages. And some people even claimed quantum supremacy. However, I think the question still remains is when, and if quantum computers will deliver the promises they have made for the advantages for industry and society. And this is a question that we will be discussing today with the panel. And we will be exploring if these are visionary promises or overhyped potentials. So I meant to introduce myself already. I'm very delighted to be chairing this session today together with Matthias. And one of the things, this is interactive, so there will be a Q&A session. Please use the, I believe there is a Q&A box at the bottom. Please use that box to post your question during the presentations. We will be following up at the end after the presentations and go through them, and we will try to answer as many as possible. Matthias, I would like to hand over to you.
Thank you, Anke. And thank you again to our colleagues from the IRP and DPG for setting the stage so eloquently. We now move to the next part of our session, where we'll hear directly from our panelists, each of whom brings a unique perspective on the current state and future direction of quantum computing. I'll briefly introduce each of them and then invite them to share a short overview of their current role and area of work. First, we have Professor Ashley Montanaro, a specialist in quantum algorithms and computational complexity, based at the University of Bristol and co-founder of Phasecraft. Professor Elham Kashefi, chair in quantum computing at the University of Edinburgh and chief scientist at the UK's National Quantum Computing Centre. Then Professor Jens Eisert, a leading researcher in quantum information theory and quantum many-body systems at the Free University of Berlin. And finally, Dr. Josef Doetsch, quantum lead at the Lufthansa Industry Solution, is working on real-world applications of quantum computing in logistics and aviation. I'll now hand it over to our panelists to introduce themselves in more detail. Each will have around 3 minutes to share their current focus and perspectives. And please, Ashley, you can start now.
Thanks very much, Matthias, and hello, everyone. It's a really great pleasure to be here and a great honor, in fact. So indeed, as Matthias said, I am working in quantum algorithms and applications of quantum computers, both at the University of Bristol and at the quantum software startup Phasecraft. So I might use a few seconds just to say a little bit about how and why I got into this field, actually, because I've been working in the field of quantum algorithms for a bit more than 20 years now. And it turns out that even back in 2004, there was already a lot of both hope and hype around about quantum computing. It was already a very exciting technology for many people. At that time, I was working in the telecoms industry as a software engineer. And I first read about quantum computing, and I read a lot of very excited articles about this. And I actually thought at the time, okay, this just can't make sense. This is all a load of hype. I can't believe this is real. And then I thought, okay, I need to learn more about this to understand if it really is a real thing or if it's something which is just some kind of scam. And then I read more and more about it and ended up getting more and more into the mathematics and the physics. And eventually I convinced myself, wow, okay, this is actually something that's really exciting. There's a lot going on here. And if I want to understand it properly, I need to actually do a PhD in the subject. And then I went to University of Bristol to do a PhD in quantum computing. And then that was really the start of my subsequent career. And then about 6 or 7 years ago, together with my co-founders, Toby Cubitt and John Morton, we set up Phasecraft to try to take quantum algorithms and applications of quantum computers into the real world and beyond just a theoretical pursuit. So it's a really great pleasure to be here today to tell you a bit about some of the things that we've been doing. So I'll hand back to Matthias now.
Thank you very much, Ashley. And then we continue with Elham.
Hi, everyone. It's a great pleasure to be here. Many thanks for the invitation. Following Ashley method, I try to also tell you a little bit about how I ended up to be here. Unlike Ashley, mine was very accidental. I had nothing to do with quantum. I'm a mathematician and then hanging around with computer scientists, and then started hearing about this random crazy quantum stuff almost 25 years ago. And just out of curiosity, it sounds super fun and totally useless. thinking that, okay, that's what we need to do. And that's where I had the great pleasure of meeting Jens also back at Imperial. But interesting about the field and the way that I evolved, that, yes, exactly like Ashley, we started with mathematics, then it was working more as a computer scientist trying to resist a physicist. But, I was hanging around with all of them. Things become more and more real, and then getting hands dirty, even with experimentalists. And even going all the way to trying nowadays, the ambitions is to really, what can we do with the quantum that make them useful? And that's my obsession. And my own research is very much focused on verification of quantum computing. I work on quantum crypto, but one thing that it might be actually very much linked to the topic of our discussion is verification. How do we know quantum computing is doing what it's supposed to do? And that has been one of my obsession along all the other topic of finding the difference between quantum and classical and really trying to make something useful of it, which of course I will talk a little bit in the context of NQCC and the work we're doing at University of Edinburgh Quantum Software Lab. Thank you.
Thank you very much, Elham. And then we go to the German side. Jens, please continue.
Yeah, thanks very much indeed for the kind invitation. It's a great pleasure and again, a great honor to be here this evening. I work in Berlin at the Freie Universität, and I'm also affiliated with Helmholtz and Fraunhofer. But in fact, yes, I did used to work in London with Elham some years ago, and I'm also a veteran in the field in the sense that I did my PhD in 2001 in the field, and my head exploded when I learned about the field when it was still young at the time. So I see my research as being located somewhere between physics, mathematics, and computer science. I like to work in rigorous terms. In precise terms, I like to prove theorems. But at the same time, I'm deeply pragmatically motivated. I have a Swedish mother, so I want to solve problems. I want to relate my theories to things that exist, to protocols that work, to existing schemes, and also to experiments in labs. And along this way, I have a wide range of interest in quantum computing, as you will see in my presentations a few seconds from now. Thanks again for the invitation.
Thank you very much, Jens. And then finally, we continue with Joseph.
Yes, well, also from my side, thank you very much for the invitation. It's a great pleasure to be on this panel of DPK and IOP. I started my journey actually in physics, but more on the side of geophysics with a PhD in Zurich, and then spent time at institutions, academic institutions in both the US, Denmark, and then also back again in Switzerland, working in geophysics. And actually, from that went into data science at Lufthansa 6 years ago. And my interest in quantum computing was more of a private interest that I did outside of work, and which then subsequently became relevant. And so for the last 5 years now, I've actually built up a team of quantum computing and optimization at Lufthansa Industry Solutions for the entire Lufthansa group, basically. And we found that the topic is so relevant and so largely discussed that we actually need to build up our own expertise to understand what is happening in the world of quantum, and to see what type of partners we need, and to judge for ourselves what type of benefit we can actually expect from quantum computing now and in the upcoming years.
So thank you very much, Joseph, and thank you to all our panelists for those insightful introductions. We'll now move into the presentation segment, where each speaker will have around 10 minutes to share about their current work, perspectives, and the challenges and opportunities they see in the quantum computing landscape. And I'll now hand over already to our first presenter, and we go back to Ashley. So please, if you can share your slides.
Thanks very much indeed, Matthias. So hopefully you can now see my slides. Actually, no, I don't think you can. I don't think I pressed the right button. Let's try that again. Okay, so hopefully now you can see my slides okay. Okay, so I decided to have as the title of my presentation the same title as the event, because I think it's a very nice title to describe the state of the field of quantum computing at the moment. So I think probably all of us are here because we're excited about the potential of quantum computing and what it might be able to achieve. And I guess we all know that quantum computers could solve some problems which are beyond the capabilities of the world's best supercomputers, and also some problems which are very important for practical applications. But I guess maybe we also all know that the field of quantum computing is at a very early stage in terms of the hardware development. And we often say that it's like the 1940s or the 1950s, perhaps, of standard classical computing. I don't know how many of you might recognize this picture, but it's actually a picture of the world's first stored program electronic computer, which is the Manchester Baby, which is the same university where I did my undergraduate degree. And sometimes it feels a little bit like quantum computing is at this kind of stage. The quantum hardware is already able to do some really useful things and things that are really straining the capabilities of classical HPC. But still, it's very tough to get those machines to do anything useful. And this is what my talk's about, some of the things we're doing to try to achieve that. Okay, so it may be kind of obvious, but it's worth stating it explicitly that if you want to do something useful with a quantum computer, then the algorithm that you run on that quantum computer had better fit within the capabilities of that quantum hardware. So at the moment, the sort of quantum hardware that we have is not fault tolerant and error corrected. It's so-called noisy intermediate scale quantum hardware. And hardware like this can only execute a certain number of operations before it gets overcome by noise and errors caused by unwanted interactions with the environment. And that means that this puts a strong constraint on the complexity of the algorithms that you can run on that hardware because they have to fit within this budget. And in some cases, the algorithms that we want to run might have many, many operations. Some quantum algorithms that are known might have more than 10 to the 12 operations in them, or even more for some things like some versions of Shor's algorithm. But on the other hand, the quantum hardware that we have today might be able to execute around 5,000 operations, like 2-qubit quantum gates, or perhaps even fewer. So that means that there can sometimes be a gap between these two bounds. And there's two ways that we can try to bridge this gap. One of them is we can try to improve the capacity of the hardware. We can try to make it work better such that it can execute more complicated algorithms. But something else we can do is we can develop more efficient algorithms to try to fit within the capacity bounds of the hardware that we have today. And that's exactly what we're trying to do at Phasecraft. People often ask me, what does a quantum software company, a quantum algorithms company do? And this is really our overall goal. And there are two areas which we think are particularly promising for near-term quantum computers to have an impact. One of them is modeling and simulating quantum physics. So quantum computers can natively model quantum mechanics, whereas to do this accurately on a standard computer, you have to pay an exponential overhead. And so this means that many problems where very accurate atomistic level modeling of a physical system is important are ones where quantum computing could be very useful. And these problems occur all over the place in areas such as designing new batteries, better solar cells, maybe better catalysts for clean energy, or even for drug design and discovery in pharma. And in all of these cases, quantum mechanics can be important, and quantum computing could be important too. And another area, which is the one I'm going to focus on today, is maybe more surprising because it's an area which doesn't have any quantum mechanics involved in it, at least on its face. And that's solving hard optimization problems where you have to optimize over exponentially many possible solutions to find the best possible solution as fast as you can. And these problems also occur in many different places, such as finance, logistics, energy networks, and many others besides. And it turns out that quantum computing can have an impact here too. And this is what I want to talk about today. In particular, I'd like to discuss something that we're working on right now, which is an approach that we call quantum enhanced optimization. And this is based around the idea that in classical computing, many optimization algorithms have a similar structure. They start out with a randomly chosen solution to some problem, and then they do some operation. And our idea is that we can try to use a quantum computer to produce a better initial guess that gets put into the classical algorithm. So rather than starting with just a completely random, unstructured guess, we start with something which has some hope of being closer to a good solution because it's the output of a quantum algorithm. And the idea is that even if the quantum computer is noisy, is affected by errors, then we can still perhaps get something useful from this because the solution gives the classical algorithm a push in the right direction. And the reference in the bottom left is our paper on this topic. And we've implemented this idea for problems to do with optimization on graphs or networks. There's a number of famous problems that have this structure. For example, there's the max cut problem in graph theory, also many others. And these have direct applications in areas such as finance and logistics. They also have a number of really interesting direct applications in energy networks, which is a particular area that we've looked at a lot. Just as one example, deciding where to position renewable energy resources in a complex energy network is one such graph theoretic problem, which this sort of approach we think is relevant to. But then it can also be used as a subroutine to accelerate other more complex algorithms as well. And what we've seen in our initial experiments, and I'm not going to say anything about how this works today, but please feel free to ask questions. What we've seen in our early experiments is that this approach can accelerate classical algorithms. So what this graph is showing is what happens when we use the output of a quantum optimization algorithm as input to a classical optimization algorithm in terms of what's the speed up factor compared with the original standard classical algorithm. So this is measuring the speed up that the classical algorithm gets by virtue of having the quantum guess as its input rather than just starting with a random guess. And the graphs are showing various different types of error mitigation that we used for our experiments on quantum hardware. And the most high performance error mitigation method that we used for the largest problems we were looking at, which were graphs of like 30 nodes in this example, the highest performance error mitigation method let us achieve a speed up of a factor of about 1,000 or so compared with the original classical algorithm. Now, this is still a small scale prototype system. Like when I say the speed up is a factor of 1,000, you should imagine the classical algorithm was already very fast, and this is just making it even faster. But still, we see it as a really promising initial step for the future. And this is actually available now. There's a web-based interface that you could look at yourself. I invite you to do that. You can go to optimization.phasecraft.io and see some of the results that we have, and also how you can apply this to some problems in energy networks. And yeah, we hope this is interesting and very interested to hear your thoughts on it. So as well as developing these algorithms and the theory behind them, we think it's absolutely critical to implement and run these algorithms on quantum hardware. So this is something we're doing as well. We're working with quantum hardware companies such as Google, Quantinuum, IBM, and Quera to actually run the algorithms we develop. We have some really interesting results, which I don't have time to talk about today. But we think that now is an incredibly exciting time actually for quantum computing because we think that the technology is really on the cusp of quantum advantage. And we also think that it's going to be algorithms that are going to get us there combined with the hardware progress. So really exciting time and really looking forward to seeing what the next few years will bring. Thanks very much. Sorry.
So thank you, Ashley, for the very nice presentation. I would say then, Elham, you can continue with your presentation.
So, okay. So, I'm trying to give you a different perspective of the ecosystem that we are trying to build at University of Edinburgh Quantum Software Lab as part of the National Quantum Computing Center to answer the question of hype or hope. So I want to show you what needs to be done in our view so that we can answer that. So this is a bit of an overall program that we have rather than a very specific research, but happy to discuss during the discussion. So I call this exploration for exploitation, and I'm hoping to try to identify a little bit about how we can manage this area and what would be the role of the academic research in this perspective. So just to also present, the exciting moment that we are all living at, so we have, particularly in almost in all the ecosystem, but particularly in Edinburgh, we are as part of the world-class ICT and AI at the School of Informatics. Of course, AI is affecting all aspects of our research. We are also the National Lab for Supercomputing, HPC Center at University of Edinburgh. In UK, recently, we have heard about the strategic vision of quantum technology, and in particular, NQCC roadmap, National Quantum Computing Center roadmap over the next 10 years to deliver quantum mission that UK has announced. So in this soup of all of these different fabric of computing, what is the mission of Quantum Software Lab that I tell you a little bit about is to put all this incredible strategically potential and trying to define a program that is science-driven in order to address the question of the hype. And just to put it in the context, maybe everybody might share this. For me, we are seeming that we are at a new scientific paradigm. There is a bit of a tension. We are all celebrating 100 years of quantum mechanics, the birth of quantum mechanics in 1925, and now we are in this international year. But in my view, this traditional linear path that the lab discovery will eventually come to the way that now is finished, and now we are reaching to the industry application, that linear path in quantum is collapsing. In a way, what is so special about quantum and so exciting about quantum, and hence hype versus hope, is that we are in the area that we are being challenged to exploit the very core foundational science in a real time, even as we continue to explore its deepest foundation. So this core tension that we are facing, for us, is a powerful creative tension. In a way, the way that we are trying to do, saying that, okay, this robust exploration fuels meaningful exploitation, and that's exactly how we believe is the science can drive motivation and giving a rigorous way to explore potential application. But at the same time, real world problems, when you talk with the partner, I will talk about, and when you're trying to really understand the pain point, it actually can inspire new avenue of research and questions. So to me, this is where this push for knowledge and pull for impact is actually make it very creative. And what we have been trying to build over the last few years is to really embrace that rather than trying to show that they are against each other. So our program, in collaboration with NQCC, is a Quantum Advantage Pathfinder program. It's a pretty standard program that you would imagine that anywhere when you explore quantum advantage you need to go. We start with industry pain point. This is coming from a very successful program that NQCC is leading, a Spark quantum application portfolio that is trying to reach out to all the end user to define their use cases. And the research program that we're leading is trying to understand, to define this problem as a concrete mathematical problem, exactly as Ashley was presenting some of them, translating them, then designing the core algorithm, try to implement them in hardware. And at NQCC, we have access to various hardware, as well as recently announced testbed program, which we can talk about later. And with this access to this combination of you can say white box hardware access, we are able to revisit this one till we reach to the level that, yes, maybe some of these things are ready to become a product, or actually the advantage that we have as scientists also identifying where there is no advantage, to clarify where is the way that there is no advantage that comes out of it. So that's the workflow that we're working. I just give you a bit of idea of few research of many of my colleagues at QSL, just to tell you how we are seeing this exploration, exploitation as two sides of the coin. They are not separated. One is the science job, one is the industry job. So just looking at the machine learning, we have worked at length to understand the fundamental question about the power of quantum data. Creating new quantum convolutional neural network architecture is some of the work we have done. But at the same time, we have also shown where the surrogate model, the classical model, actually can simulate what quantum can do, and hence there is no advantage. So we keep trying to pinpoint exactly where is the advantage coming from, and using that, recently we also work on the quantum enhanced generative AI. And once we have done with our science, at the very same time, the same topic are the one that we are collaborating seamlessly with a partner like HSBC to exploit those framework architecture, QCNN that we're designing for fraud detection, or we're working with the colleague at Genomic Lab trying and the quantum-based alpha to trying to tackle the particular healthcare challenges that they're bringing to see if our framework of quantum enhanced generative AI is relevant. And this continuous benchmarking against the classical state of art is trying, although sometimes it's very exhausting, because you see that in fact classical AI is also very powerful, but it's clarifying where the advantage can be obtained. And that's one example. Another idea, in order to make sure that we're really getting quantum advantage, another pillar of the work, of course, is error correction. So on the science part, my colleague have been working a lot on novel quantum LDPC code and decoder that were previously just theoretical constant. In fact, it's a collaboration between QSL and Jens' team. And at the same time, this has led to an open source LDPC software that is now foundational tools that is used in all of the industry as the toolkit that help them to explore fault tolerance. So again, another example that how the science at the core of creation is become utilized by the industry, which makes me very excited. Another topic which is much closer to my own research, as I mentioned, is regarding verification, trust in theory, trust to the hardware. So there is this question of, as our hardware is scaling up, if we are going to the level that they are no longer classically simulatable, when we're talking about 1,000 logical qubit devices that are emerging, then you need to have some notion of how do we know that it's actually doing what it's claimed to do. And this is a very, very hot topic right now. And there are many, many different benchmarking toolkit that exist, but over 2 decades, we have been defining this very much theoretical toolkit of heuristic-free scalable benchmarking technique and formal framework for verification and error detection and error correction. But they have been very much theoretical, and very recently we try to push this thing to actually something that can be implemented and can give some trust and guarantee on the platform. And the very recent work, it was translation of this theory work to actual implementation on the Quantinuum platform, which is an on-chip verification that is making the minimal assumption about the device, minimal assumption about the noise, minimal assumption about the architecture, but it allows us to actually certify the platform is doing what it can do. It's very much linked to a recent work, for example, we saw from our colleague at Google that as well put the verifiable quantum advantage forward. And this is now a core of the testbed program of NQCC, which we have now several different platforms, and we want to provide this robust certification that is algorithmic agnostic, hardware agnostic, noise agnostic, and gives a level of trust to deal with the hype that we might see from this platform. To move on, security is another area that, again, for us is also area that you can think about quantum advantage. We are exploring, again, in theory, multi-party quantum computation, various notion of secure quantum cloud computing, blind quantum computing that we have been working, again, in a very theoretical world. But now we have reached the level that these theoretical work are becoming part of architecture. Very Cloud is a startup that I co-funded, and we have put a two-line architecture that makes this theoretical work to be something that is now as a level of the device plug and play readiness to provide security for the emerging quantum platform. As well as in parallel, we also has network security in quantum future, which is trying to make sure that we have a tracker. This is more related to the power of quantum algorithm regarding post-quantum cryptography, that how could we do a resource estimation? So when we're looking at the critical infrastructure, we can make sure that we are tracking the evolution of our quantum algorithm where we're standing. Final few topic of HPC integration. Our colleague has been defining very, very high level language in programming languages in order to deal with the integration of HPC and quantum. And now sitting at EPCC, which is the National Center for Quantum Computing, this level of language are now being really integrated to make sure that the offloading, the proper quantum task offloading for using this open source software can be integrated with the quantum hardware that we are hoping to integrate with. Maybe I just jump to one last one about saying that this exploration with exploitation really works, and it's not just ad hoc, because XPRIZE, some of you might have heard that this was this recent initiative that is quite nicely exploited. However, where can we see the quantum advantage, but from application point of view? And some of our colleagues, in fact, is really student driven. We're very proud of our three of a student who were digging into the fundamental question of efficient quantum state preparation, removing bottleneck in simulation of thermal ensemble of a coupled harmonic oscillator, but they are actually hook up with the Q-Control team as our industry partner, and they made it to the semi-finalists in the XPRIZE, which is giving us any hope that indeed this exploration in the science actually can bring concrete advantage. So in short, just going to wrap up. So what we're trying to do, and I think this is the way that our field can deal with the landscape that is emerging, is continuously creating the triangle between science exploration, technology implementation, of course, as the hardware and various components are emerging, as well as understanding the very useful use case exploitation. So we are not just doing the science in separation for this advantage. And I think these are all influencing each other. And what our goal is, coming back to the international aspect that Tony was saying at the beginning of our session, we truly believing that it's not the job of one nation, one lab, or one place to completely understand. So we're trying to create this global Scottish enlightenment. It's really, we are having many worldwide partners, and the foundation support of the UK ecosystem in order to drive the science, not thinking that the science is done. So we are very grateful to EPSRC, NQCC, and NQTP to embrace the long-term investment in research. But it's also the most valuable asset, in my view, at this moment, is the brilliant people which are driving this innovation. And the shared mission is to really trying to bring all this notion together and defining this quantum future that we are all exploring together. Thank you very much. I stop here.
Thank you, Elham. And thank you for the comparison between showing the scientific exploration and the exploitation at the same time. I think it's nice to see them together. Thank you. Just to remind everybody who has questions, please put them in the Q&A box at the bottom. We have one question so far. Don't hesitate during the presentations to put your questions in there. I would like to move on to the next speaker, to Jens, please. Please go ahead. Thank you, Ellen.
Yes. Thanks so very much indeed, again, for the kind invitation. I will use my 10 minutes to say a few words on the very much substantial, as I think, potential, but also some limitations of quantum computing that we presumably should have on the radar. So the idea of quantum computers, of a quantum computer, is not so much of a new idea. Already in the 1980s, people like Benioff, Doetsch, and Feynman were contemplating quantum computing as a purely conceptual abstract idea. But only in the last 7 or 8 years, protagonists actually set out to build such devices to a reasonable scale, a lot driven by the US tech industry, but also by players in Europe and in China. So surely the machines we have today are not huge, but and they're also still somewhat noisy. But then quantum computers of that scale and precisions were completely in the realm of science fiction until quite recently, which creates a hugely exciting state of affairs. And the question is on the desk whether we can reasonably hope realistic quantum computers to provide a speed up over classical computers. That's an interesting question. It's a big invitation that creates expectations and also somewhat like exaggerated expectations sometimes here. This is from a report by McKinsey that was anticipating revenues up to like $2 trillion by 2035. This other article was on the front page of Handelsblatt. There's a German newspaper saying that quantum computing would rapidly speed up all processes in the world. Is this so? Well, not quite. I mean, we do know, say, a couple of dozens of quantum algorithms that do show a super polynomial advantage over classical algorithms, or the best known classical algorithms for the same problem. And we have all the reason in the world to be very much excited about this. At the same time, if you read the popular press, it's a lot about applications of quantum computing in machine learning, in optimization, in quantum chemistry and materials. And if we are honest about this, we do not quite know as much as about this type of problem as we would like to. And here I'm also picking up a topic that Ashley has so nicely put forth at the beginning, because these are the type of problems that, as we speak, are being developed all around the world, picking up a point of Elham. And then I will use the remaining few minutes that I have to say a few bad and a lot of good news along this way. And let me start with the bad news. We know that noise is the main enemy of a quantum computer. It makes the system less quantum and more classical, and this kind of precious quantum advantage presumably goes away. So for a non-quantum error-corrected quantum circuit, a random circuit, you can do a deep quantum circuit, but then you cannot, because actually it turns out that all you have is a logarithmically deep shallow circuit. And at the beginning, you can put in nothing or your birthday or something. It will not matter. All you have are logarithmically deep quantum circuits. Then there is a portfolio of techniques called quantum error mitigation that would largely undo noise on the classical level of post-processing as a body of beautiful ideas along this way. And then you can ask, great, but how far can this go? And then you find as a mathematical theorem that there are strong obstructions against error mitigation already at log depth in worst case. So there's the mathematician's joke that log is upper bounded by 4. It's a very good joke when you think about this. And I'm not saying that error mitigation does not work. It does, and it should and must be done. It increases the circuit volume in a nice way, but it's just not scaling very nicely. But there is no reason for panicking whatsoever, because the circuits we have today are also very good. The average gate fidelities are high, and the errors are of the order of 10 to the power of -4. So we can already, as of today, do quite deep circuits. And it's our job as a researcher to kind of find the sweet spot and see what types of utility we can think of when we have devices of that kind available. But it's good to know the precise limitations. If you are willing to do quantum error correction, one can do, in principle, an arbitrarily long, perfectly precise, sustained quantum computation. And the core idea is that you do smart measurements, and using them, you find out about the error, but exactly nothing about the precious logical information that's being encoded in the system. And I say in principle, but actually, even within the last year, so much has happened along the lines of research of quantum error correction. It might well be the field in quantum computing that's most rapidly and drastically developing, with lots of ideas in theory, in experiment. Here's an example of our work where we looked at quantum codes that have very attractive features and are in a precise way optimal, so-called qLDPC codes. In fact, Elham has mentioned this just a second ago, which are beautiful codes with highly attractive features, but it was not so clear how to do actual computing with them. And what we found was versatile, accurate, and precise, fast decoders for such codes to make them actually practically useful in practice. In fact, as in a collaboration with our friends in Scotland, as was mentioned a second ago. The biggest hurdle in all of this is to think more of quantum software. Quite frankly, we do not quite know as much as we would want to what quantum computers are good for. And this is something we really have to work hard. And again, along these lines, a lot is happening as we speak in these days. Here are two examples of my team, like a bit along the lines of what Ashley has said. And the first thing is on machine learning. It's hard to deny that machine learning is changing the world we live in. I'm sure that most of you have used ChatGPT a number of times today. And of course, it's a reasonable and in fact important question to see whether quantum computers can do better in meaningful machine learning tasks. And indeed, the answer is yes, they can. There are super polynomial advantages in machine learning, say in families of generative modeling, such as diffusion probabilistic models, or in the training of sparse pruned classical networks using quantum techniques. In other words, quantum computers can contribute something to meaningful machine learning tasks. Or take optimization. That was the core topic of Ashley, where it's clear that in all kinds of scheduling and routing problems, and maybe from Joseph, we will hear more about that in the aviation industry, some sort of optimization problem will be involved. Unfortunately, they are usually difficult. They are NP-hard and worst case complexity. But what turns out to be true is that there are settings where you can find efficient quantum approximations of instances that are hard to approximate on a classical computer for problems like integer programming or so. Google has just followed up along these lines with ideas of decoded quantum interferometer, which are beautiful ideas where, again, you find that a quantum computer can approximate instances well that are hard to approximate on a classical computer, which shows that there's even hope to see quantum advantages in optimization in a way. But then for the years to come, presumably the most likely area of quantum advantages that in quantum simulation, where you go into the lab, not me, don't let the theorists into the lab, but you simulate, integrate quantum systems under highly precisely controlled conditions. But one kind of new way of looking at it is this one here, where you can go into the lab, you can take data, but you can use these data to very precisely understand what you have, what the Hamiltonian is in the lab, and then equipped with this knowledge using ideas of Hamiltonian learning, you can make predictions, but equipped with much stronger predictive power because you know what has been happening. This work has been done for and together with our friends at Google, calibrating the Google Sycamore chip. Which brings me to the end of my presentation. So this is done in Berlin in a large and fun team that's driven by a great discussion culture, by lots of time on the blackboard. We're also very happy to see generous funding by our funding bodies like the German Ministry for Research, Technology and Space, or the European Commission and the flagship programs, the DFG, or I'm very grateful, I should say, about the generous funding by the European Research Council, in that I have a beautiful advanced grant on this subject here. To conclude, so this was somewhat superficial, but together with my colleague and friend John Preskill, we recently sat down to kind of see where we stand and put out like a perspectives article on where we are in quantum computing, identifying like 4 fields of mitigation, correction, algorithms, and simulation, see where we stand and how we can take meaningful steps from the noisy intermediate scale quantum NISQ regime we are in at the moment to the fault tolerant application scale quantum regime where we want to be in. And this is a long and winding article. I would be super happy to read the final quote of this article because it picks up a line of thought of Ashley. I might do this later. I have the time. Overall, I think we have all reasons in the world to be excited. I would say as long as we stay away from the hype and take our steps carefully, step by step, to overcome the gaps between this NISQ and the FASC world, then all will be well. And on this note, I thank you very much for your attention, and I'm very much looking forward to the questions you have in the questioning hour. Thanks so much.
So thank you very much, Jens, for this insightful presentation and also what we can expect and what we maybe could hope for quantum computing. And next we move then on to Joseph, who will give the final presentation.
All right, I hope you see my slides. Thank you very much to all the previous panelists that have set the stage and gave us a great overview of where we stand in the industry or with quantum computing. Now, I'd like to add another perspective, and that of the end user. As Lufthansa, we are not developing quantum computers. We're not planning to develop quantum computers, and we weren't actually planning to dive into quantum algorithms even. Now, we have started to look into our quantum algorithms, not actually developing new ones, but at least looking at those that are around and seeing how they actually apply to the use cases and problems that we find within our organization. Now, Jens has shown, just 2 examples of mainstream media covering some breakthrough in quantum computing. And in recent years, or just this year, I think at least 5 or 6 of those breakthroughs that have been covered by mainstream media have made it to the attention of our management. And that's why we actually decided as our quantum computing team, or also within our organization, we actually need to build up the know-how to judge for ourselves when one of those breakthroughs is achieved, and we see all the media coverage, to judge for ourselves what does it mean for quantum computing and what does it actually mean for our organization. Because oftentimes it does imply that, yes, all processes are suddenly a lot faster. So then the question is, well, why are we not using them if they already do that? And of course, the reality is a lot more nuanced. And so we started having regular briefings to different parts of the organization, different parts in the management, to actually then bring them on board and work together with us to find out how we can use the current state of quantum and what we actually need to do, what type of capacity we need to develop in our organization to use what's out there efficiently. Then security, I'll speak about that in a moment, but this is of course one of the main fears, that our current communication may not be safe in the presence of large enough quantum computers. But then on the positive side, really, we are looking at use cases and trying to find those use cases where quantum computing will give us some type of advantage compared to classical computers. And last but not least, cooperation is really what we are trying to set up now at the early stage of quantum computing to then have the right partners once there is advantage to be gained. Now, for post-quantum cryptography, or generally moving towards post-quantum cryptography, we actually find that this will be the new standard independent of the development of quantum computers almost. So our current encryption may be broken by quantum computers, but post-quantum cryptography is around already. And the beauty is that we don't actually need quantum computers to set up that post-quantum cryptography. So we can start our journey to post-quantum cryptography now, and we are seeing from the security offices in most countries actually that they are recommending moving to post-quantum cryptography now, and that this will happen within the next 5 to 10 years, that there will be compulsory even to move to those. So even without hope for quantum computers being strong enough, we see that this move to post-quantum cryptography is happening, and that we better start now rather than later to actually do our inventory and start that journey towards PQC. Now, really the main focus for us is use cases. And I'll illustrate a few of those. The first one here, well, you'll all know the situation that you actually land in a plane. That plane is actually on time, but then you'll have to wait in the plane because that gate is for your aircraft is not ready. Finally, your aircraft gets another gate, only to find out that the path to your connecting flight is super long. Now, wouldn't it be nice to actually have all of this optimized? And this is one of the use cases that we're looking at. And of course, there are classical implementations of this gate assignment problem. And that's what we're actually doing. We're using state-of-the-art mathematical solvers and classical formulations to actually solve that problem. Benchmark the classical solution, and then see what quantum computers could actually be doing here, and where there could be a benefit. Actually, in the case for the gate assignment, even though the number of possible assignments grows exponentially, runtime of the best classical solvers scales almost linearly with the number of flights, as long as you're not taking transfer passengers into account. The moment you actually are optimizing the arriving and departing flight at the same time, you have that quadratic term in there, which makes perfectly to an Ising model or qBOS in general. And in that case, actually, classical solvers, suddenly you get an exponential increase in the runtime. Now, in another project, actually, with the German Aerospace Center and also our partners, airlines Lufthansa, Eurowings, but also qBIG Quantum as a quantum startup, we are actually looking at the entire planning cycle for airlines. So aircraft rotation, basically which type of aircraft is doing, which aircraft is doing which round trips, then the tail assignment, so choosing a specific aircraft for specific flights, disruption management, especially for crews. What do we do if a captain gets sick the day before a duty? How do we replace? How do we reshuffle everything? And then also flight route planning. And this is actually a research project to look at the potential of quantum computing in aviation with all of these partners. And just a glimpse on one of those. For the flight path optimization, it's a complex problem, basically on a graph, and there are efficient classical algorithms actually to solve this, as long as the complex air traffic control constraints are not taken into account. So currently, yes, of course, there are classical solutions and every flight is optimized, but there's no guarantee that we are even close to the optimal solution. And especially, we have these long-range interactions. So a decision very early on during a flight may actually or does have an impact on the decisions late in a flight. And this is something that classical algorithms can't handle very well. We're investigating if and how quantum computers could actually help here. Now, how do we do this? We have a team that actually handles or works on both quantum computing and optimization. And this is actually something that we found while looking for optimization problems that are difficult classically. We actually find that there are a lot of optimization problems in our organization which are currently not optimized at all. So oftentimes we actually do the classical implementation just to see in a way if there is any hope for quantum advantage here. But that classical solution actually gives us a lot of business benefit already now, independent of a future quantum computer. Now, and then last but not least, cooperation is really key here. We're a partner in qTech, the German industry consortium, and actually working in depth on algorithms, on the code to develop those use cases jointly, and then also the partners mentioned previously. All right. Thank you. Looking forward to the questions and discussion.
Thank you. Thank you very much for all the panel and very interesting presentations. I did learn quite a bit. I'm not a quantum computing expert, so thank you. I would like to move on to the Q&A portion part of the session now. And please, I remind people, place the questions. We've got now 5 questions in the Q&A box. Don't worry about if you're an expert or not. Anything is welcome as long as we can help you out with it. I will start with the first question. That question is to Ashley, and it's from Miriam. And Miriam wanted to know, what is the difference between quantum enhanced optimization and quantum optimization algorithm or quantum annealing?
Right. So first thing I should say in answer to this question is that there is no standardization really in the field on terminology. So I'll just say the way in which I would use these terms. So firstly, for me, quantum enhanced optimization is using a quantum computer and a quantum optimization algorithm to enhance a classical optimization algorithm and not to replace it completely. Other people do not use it to mean that. Other people use it to mean to replace the whole of the classical optimizer. The quantum approximate optimization algorithm, QAOA, is a particular algorithm you can run on a quantum computer, which is targeting today's noisy quantum computers and is designed to be efficient for those and sometimes performs pretty well. And finally, quantum annealing is a technology which is a bit different to universal quantum computing. Quantum annealers are special purpose machines that use, they still use quantum mechanics, but in a somewhat different and more special purpose way than general purpose quantum computers to solve optimization problems. So yeah, that's the brief synopsis, I think.
Thank you very much. Right, Matthias, you want to take over the next question?
Yes. There's the next question regarding quantum hardware, because we have now seen a lot about software and applications. But the question is, and addressed to Jens. So why do you think the people in the community don't invest enough into topological quantum computing?
Okay, there's a lot to say about this, but I will keep it short. Yes, there's different architectures for doing quantum computing. They're like vastly different, and I'm being asked a lot, like, oh, which is the best platform? Why don't we invest just in the best platform and then we just would defund all the others? It's actually not so easy to see. For reasons I'm happy to explain which one is the best. That said, it can make a lot of sense to invest a lot into a good qubit, if that might mean that the overheads in quantum error correction would be reduced because the qubit is kind of better. And this is the promise of topological quantum computing. In fact, I'm now at FU. I spent the day at a CSC meeting that was dedicated to topological qubits. So that was my day work for today. This is a compelling idea that you run a qubit that is already topological to start with, is protected. And there's a couple of ideas with my runner fermions that would produce topological qubits of this sort. This is a very beautiful idea. It turned out to be quite difficult. I was present at the IPS March meeting talk by Microsoft, and I'm extremely grateful for them that they actually do pursue it. So that it's not quite true that nobody is investing a lot. Microsoft is investing a lot of resources, ideas, funds, and everything into getting topological Majorana fermion devices going. The trouble is, these devices are extremely fragile, not so much to environment noise, but to a disorder of the system, and it's far from clear whether this will work or not. But it's absolutely worthwhile trying. And the last word hasn't been spoken. some people do it, and if Microsoft does it, it would be, I mean, it's a wonderful thing, and if they make it, that might be a good qubit. But it's surely not the easiest way of getting it done. And people have like accepted that you can do a lot on the software level. You just have your qubit and you do all the rest on the software level, running fault tolerance and quantum error correction. It's a bit like Tesla. I hope Tesla builds cars. It's like a software product with a bit of a hardware thing, which is the car. So then some people think of quantum computers as like some hardware that you take as you have it, and then you put like a sophisticated software package on top that does all the decoding, error correction, fault tolerance scheme, and so on.
Okay, well, thanks very much, Jens, for the insights. And Anke, I would hand over to you.
Thank you again. So there's another question to Ashley. This is about a graph you have shown earlier on in your presentation. And there was a question on what do you mean on your x-axis? What do you mean with complexity?
Yes, so this is a very simple family of graphs. It's just lines of different lengths. And I was solving a very simple problem on these graphs, which is the max cut problem, which has an exact answer that you can write down easily. But the classical algorithm that we were using to solve this problem it doesn't know about this answer, and so it does take increasing amounts of time to solve the problem as the problem size increases. So it's sort of meaningful to look at different sizes as a benchmark and to see how much that classical algorithm gets sped up by the quantum algorithm, by the quantum input. I should say that these results are all in our paper, which, if you go to optimization.phasecraft.io, it's linked from there, so you can take a look yourself.
Thank you, Ashley. Over to you, Matthias, again.
Yes. So there's a question to Elham regarding quantum machine learning, because the question is, so where does quantum machine learning based on quantum data, so not classical data encoded in quantum states, stand today? And is there actual hope of an advantage over classical?
It's a very good question. I think maybe it's not as explored as the idea of following with the classical data, because we want to have those classical benchmark against what classical data and classical AI is doing it. But in some area, if you wish, the quantum data, for example, the noise of the devices, when you're looking at it for calibration of how we can actually understand. So these are quantum data, but we use, in reality, classical AI for currently, they're doing a very good job. So it's not using quantum machine learning with the quantum data, we're using classical machine learning for quantum data to solve it. But moving forward, some of the element when we were looking at the genetic data, Gen AI, is the area that we're using a little bit like in the same framework that Ashley was showing, that we're using quantum computer to produce the quantum data or quantum simulation. And then you're trying using that, try to do that. Either you plug it to the classical pipeline or you plug it to the quantum pipeline. So this is one area for creating the more enhanced quantum data, especially when you're talking about the higher order simulation. Another area that we have been playing is regarding quantum cryptanalysis. Classically, you can use classical AI to actually show and figure out the side channel attack and vulnerability. But when you deal with the quantum protocol, and you have quantum data communication between your party, and that's very natural that you need to have using quantum machine learning techniques to actually figure out what are the parameters you need to access. So people have to start using quantum machine learning for the quantum cryptanalysis. These are a few examples.
Well, thanks, Elham, and Anke, to you again.
Yes, this is a question to Joseph. Are there already classical post-quantum algorithm implemented in standard libraries like OpenSSL or libSSL?
Yes, they are. I think for OpenSSL, it's since version 3.5 or so, it is available. Also, all the major cloud providers are either on their way or have post-quantum cryptography available already, possibly in their beta versions. But this is certainly so. Last year, 2024, the US National Standardization actually standardized or the first algorithms, and those are now being implemented. Most of them are already available.
Okay, thank you.
Yes, so we do have a question from Frank Schwab regarding so-called magic states. The question is it correct that, oh no, so 1 second. Yeah, that a real working quantum computer would need so-called magic state that cannot be generated with error-corrected qubits. And Jens, maybe, I mean, you might add to this.
Well, yes and no. I mean, so what is a magic state? So I mean, in quantum error correction, there are certain gates that are particularly, say, easy to implement. Say in surface codes, these would be like circuits from the so-called Clifford group that would be transversally implemented. That's a certain group of operations that's not computationally universal in the sense that you cannot do an arbitrary computation, but just some computation. And that's very difficult to overcome. The idea of magic state distillation is that you create extra ingredients, so-called magic states, that you put in through gate teleportation, and then you uplift the Clifford circuit to a full universal circuit. The trouble is these magic states are where they cannot be easily generated. They're noisy themselves, so you are using noisy stuff to make something error corrected. And the idea of magic state distillation is that you take noisy resource states, you make them pure, and then you teleport in the pure magic states. It's a beautiful idea, but this is relatively costly. That's right. Although there's a beautiful article that has even the title saying that magic state distillation is not as costly as you think. And there's beautiful work also by Greg Gidney and also by others that show it's actually not so bad. So yes, magic state distillation protocols play a role, and yes, they do generate an overhead. It's not catastrophic, and it's also by no means the only one of getting a fault-tolerant universal scheme. There's also other schemes through code switching or so that would also give universal schemes, not resorting to magic states. So I think no reason to panic, but one should be aware of the fact that error correction does provide overheads over not quantum error-corrected computation that can be quite stiff.
Thank you.
Then there's another question. This is to everybody. What is the status of commercial cloud quantum computing via hyperscale? Is there anybody who would like to answer that question from the panel?
Can you repeat the question? I missed it.
What is the status of commercial cloud quantum computing via hyperscale?
Via hyperscale.
Scalers, sorry. If the person who asked the question, do you want to clarify this? What do you mean by hyperscalers?
Hyperscalers.
Okay, let's move on to the next one. Let me see. Sorry, Matthias, have you?
I have one. Yeah.
So at the same time.
Yeah. So there's an interesting question in my opinion, because the question is, so what would be the scale or the size of a useful quantum computer? And the question is, will these massive devices be as big as, say, the Atlas detector at CERN or larger? Will that mean that access to these computers is very expensive and limited? Are there other options to build quantum computers that doesn't expand to massive sizes? So what's your guess on this? And is there anyone from you who want to answer?
I can start, but everybody can comment. I guess currently what we are seeing as the roadmap of the major hardware company is that indeed the scale that we need for the logical fault-tolerant useful quantum computing, as you've seen, is the order of 1 million of logical qubits, unless there is a crazy breakthrough on the error correction that can reduce that, or magical breakthrough like what you're seeing that Phasecraft and other are doing to reduce those requirements. We are looking at maybe not CERN, but the structure that it's require data center HPC to integrate, to provide the decoder and even the control. So these are going to be very massive. And indeed, the question of how to get access, who will get this access, what would be the model is all comes back to the industry model for it. But they are very likely, what we're seeing right now, there are going to be the cloud access and in this massive data center, especially built up to fulfill the requirement of the current development. Mm-hmm. Should things change? Maybe. Yes, you might want to add.
Jens.
No, I can only endorse that. In that, of course, quantum systems are very small, and there's this prejudice that this would mean that the devices are very small, but there's little evidence that this should be the case. I mean, if you've ever been to the labs of Google, say they have like 11 fridges next to each other, is the fridge and the fridge and the fridge. These are massive devices already for the relatively small systems that they have now. And if you want to go to 1,000,000 qubits, these will necessarily be 1,000,000 qubits. And you shouldn't forget that not only the quantum computer will be large, but it will always be a triangle of a huge quantum computer, a massive classical computer center, and also a nuclear power plant on the third part of this triangle. Maybe not so much in Germany, but in other places. The classical computing should not be underestimated because there's all this decoding work and this control work that's running against the quantum noise. So there's this famous saying by Watson, one of the founders of IBM, saying that there's maybe a world market of 5 computers in the world. And how wrong was he? I mean, clearly there was the whole business that they have IBM, but there might be a world market of 5 quantum computers. I mean, there's some evidence that this will be cloud-based, and then, of course, we have to think how to make this fair and accessible and so on. This issue will presumably emerge.
So I think Elham and Jens have given an excellent description of how things look in the fault-tolerant era of quantum computing. I guess the only, question one might have is, whether you can do something sooner than this in the sort of noisy intermediate scale quantum era that we're in now. And I guess I would argue that we're already seeing the start of the use of quantum computing for scientifically valuable problems within this time. And the question is how practically and commercially relevant we can make them within this time frame. And we're pretty optimistic about this. I mean, it's tough, but we think it's going to be possible. But I think for me, this is a key dividing line, because if you don't do fault tolerance, or if you minimize the amount of error correction that you need, then it radically reduces the cost of the of the hardware and the number of fridges you need and the size of facility you have. So the more we can do on that front, the better.
Okay. Thank you. I would like to move on to another question. This is about somebody is asking, so if you're new to quantum computing, which sort of early application should you be exploring to set yourself up for the future of a quantum computing sort of a system or environment? What should you be exploring now?
Whatever you like, depending on your expertise. If you're industry, you need to look at the pain point that is more interesting for your thing. If you're academic, you need to look at the expertise of the area, whether you are in number theory, your optimization, your machine learning. So I think the floor is open. There is no limitation, and there is not also the same way that Jens was saying that we don't know which hardware is the winner. We also not really know which application is the winner. So I feel it's really bringing the expertise that you have from the classical domain and trying to understand how quantum can enhance that. That's the good start if you want to come from that area. But if you're coming just from learning quantum algorithm is the right to start.
I would agree with Elham, because I would say it's a different answer if you're asking because you're a user of quantum computing and you want to understand which applications are the most promising, or you're someone who's maybe a student who wants to get into the field of quantum computing. And if you're in the second category, then I have to say that for me, going back to the classics is a good idea to start with, and learning some of the fundamental algorithms of quantum computing, like Shor's algorithm, Grover's algorithm, these sort of classics from the 90s, because I think these are a really good way of getting to grips with the model and how it works. But if you're a user, then you should, as Elham says, pick the application that's most important to you.
Okay, thank you.
Okay, thank you.
Just adding to this,
Joseph,
I mean,
please. Yeah.
From the user perspective, I mean, I fully agree with all what you said, but at the same time, I also feel that even as a user, it does have a lot of value to actually dive into the algorithms already and trying to figure out. And I think, this is really unique how closely actually application and new algorithms are thought together. Look at DQI, the decoded quantum interferometry. That it's a new algorithm that was first published last year, and industry is actually looking at this and trying to figure out, how can we actually map our problem to this satisfiability, source art, and so on, and to get any type of, or to get any quantum advantage. I think this is what's so exciting here, that the gap between, new algorithms and trying to bring it to application is getting super small here, and that we actually have the chance, even as on the application side, to actually work very closely with what's happening in the research.
Mhm.
Okay, thank you. So I think we have now also a clarification for the earlier question. Namely, I mean, the question is about a status from for accessing quantum computers from at home. So, I mean, can any one of you say more about, I mean, the quantum cloud service that are offered by hyperscalers like Google, AWS, and so on? So, I mean, what's going on there? Can you access this from at home?
Yes.
Yeah, Jens, please.
No, I have not so much to say about this, but the answer is yes. I mean, different companies have different philosophies and so on, and different payment systems. Many of the services are free, others are not. Yes, I mean, there is already an existing culture of cloud services that you can access stuff from home, and like there's small systems available at IBM that you can play with. That's for free. I mean, go for it. It's fun.
And in the end, I guess I would add to that to say that the thing that really differentiates different quantum computing hardware platforms is the hardware itself. It's not so much the interface that you get to the hardware. And, there may be subtle differences in terms of pricing models, as Jens says, and user interfaces and so on. But, the companies like AWS, Azure, and so on, like they're providing access to these platforms, which may or may not be ones that they're working on themselves, depending on the company. And so, I would say it's the choice of platform that's the key differentiator, and not the choice of which hyperscaler you want to go with.
Mhm.
Okay. So there's another question, sort of a bit linked to hardware and software. So there's somebody who would be interested to see the future of quantum programming and compilation. I would not suspect that GPUs will be available in the same way as GPUs. QPUs will not be available in the same way as GPUs. So how will you integrate quantum hardware into our software? So what changes do you will see? Anybody?
There's a lot of work is already being done on that. I mean, you already mentioned qDO, and NVIDIA is actually introducing the quantum version of it, but they are not the only one. So the integration to HPC that we were discussing earlier is an important one. For example, my colleague at EPCC, High Performance Computing at University of Edinburgh, they're actually believer on open source C-based infrastructure rather than any other structure. So this is very hotly debated, because we need to create the right interface between, fast calibration that you require, that is matching with the offloading of HPC versus the fragility of quantum. So this is a very active area of research. And indeed, it is you need to explore it to figure out which one you want to offload to quantum, which one you want to upload to your HPC. As well as the distributed architecture is also coming to the picture, because nowadays we know that for the scalable fault-tolerant quantum computing, we need to look at the modular architecture, how to orchestrate this modular architecture on the quantum level and classical level. It is a very, very important area of research that many colleagues now working on high-level quantum programming languages, as well as the integration with HPC.
Okay, thank you. Thank you. If nobody else has heard, I move over to Matthias.
Yeah, maybe. I mean, then one future question or follow question about the future of quantum computing in 5, 10, or 30 years. And maybe Joseph, I mean, do you think there will be a quantum computer in an airplane in 30 years?
Well, I think suspect following up on what both Elham and Jens said on the size of quantum computers, I don't expect that we will actually have them transportable. I would rather expect that we access them through the cloud if they're available. Yeah, there's so much to that. But I mean, honestly, like for where we stand in 5, 10 years, I mean, I let the experts speak, but I think the whole field, and also from the application side, we're trying to get ready to use whatever is available.
Okay, thanks. But maybe someone else wants to add about, the future of the field.
Full of hope, if you ask me. I'm optimistic. I've spent the last 25 years of my life on this, so I have to be hopeful. So, but I think Ashley put it very nicely. We are realistic that, hardware requirement are yet is not the same match with the software requirement. Jens said that we still don't know actually what are the software is useful, but these are very active, leading researcher, leading company are working on it. So I think as long as everybody keep this collaborative space, it allows me to be hopeful. There is lots of progress are making it there. So I can just say that, I don't know exactly those timeline of 5 or 10 or 30, but the co-design and co-development of hardware, software can allow us to eventually see something that is definitely beyond the classical computing. That's for sure, but also start influencing in a utility scale, as Joseph was mentioning. So I think the next 5 years is going to already give us some answer to be even remaining more hopeful, but we need to manage the hype as well.
I mean, one should also be aware of the fact that like reaching a quantum advantage is not a one-off thing. I mean, you can just do some sort of random sampling scheme that proves a wonderful quantum advantage on some like theoretical computer science underpinning, but is of no use whatsoever. Then you can say you can put in some sort of utility flavor into it. There was this recent experiment on out-of-time ordered correlation functions that already have like some learning flavor concerning quantum chemistry systems. And I think it's a step-by-step process where things become more and more practically applied and the practical utility becomes more and more dominant. And let's see, I'm quite optimistic that in the next 5-10 years, we will see exciting developments.
Yeah, I fully agree with those points. And I think I'd say that for me, within 5 years, I think we will see quantum computing recognized as a really useful tool for scientific discoveries and other practical problems as well. And in like 10 years time, 20 years time, it will just be another tool in the toolbox. I mean, sometimes some have said it will be the telescope for the 21st century, and I think that's the sort of potential that we can see.
Thank you. We have 3 more questions here, and I think that may probably need to come to a close. 2 might be quite quick. The last one we have seems to be a little bit more complex. So, okay, the first one is anyone familiar with the details of a topological qubit that Nokia is making?
I can make it very short. I mean, topological is a mathematical like property of delocalized information. That's quite similar to what the Microsoft people are doing. I mean, the Microsoft people are doing like Majorana zero modes. What Nokia is doing is what is called a supercooled electron liquid, which is on the formal level quite similar, but it's a different flavor of a topological qubit based on the fractional quantum Hall effect that is on the highest level somewhat similar to what the Microsoft people are doing, but in physical details, different.
Okay, thank you.
Yeah. And we have one additional question regarding AI, right? Because the question is also, is AI useful for code development in quantum computing? So is it used there already, or also for the design of the quantum computing hardware?
Absolutely, yes. I briefly mentioning is AI is one of the main tools that is helping in the design of the hardware. In fact, for me, quantum and AI are another fabric for computation. We need to very much clarify when do we need the classical AI, when do we need the quantum AI. But classical AI is currently helping in the error correction and the error detection, is helping in the calibration and characterization of the noise. And as we scale larger and larger, AI is becoming more useful till today.
Okay, and then there is a question which I think is a bit more complex. So it starts off, how does quantum computer work exactly? And here's a question about the non-cloning theorem. Does it mean there is no copy, paste, or duplicate on a quantum computer? Or is it only used for other types of operations, computations? Or are quantum computers actually hybrid?
Indeed, it requires another hour of discussion. So
That's
yes,
right.
in short, we don't have a copy and paste, and that's why it's actually why quantum is super exciting. But I think it's going to be misleading. So quantum no cloning is one of the main principles of the quantum mechanics that quantum computing need to follow it. But it also is a feature that we will use in order to provide security and other thing. And there is some other approximate cloning, etc. So it's a whole area of research we can talk forever about.
And is there maybe an easy resource for somebody to look at this? Any good resources you might be able to recommend people to continue?
Actually, if I may say so, like picking up on line of thought that Ashley has said, I mean, the good old Nielsen Schwang, that was written in the 90s. It's unbelievable, but it's still a pretty good book. I mean, you put some dust away, but I mean, they had so much of a vision of what is there to stay. Other hypes came and went away. This is still good stuff. And I mean, read Nielsen Schwang and you know what's going on.
Thank you.
And I would also add for anyone who's interested in, let's say, the somewhat more foundational and philosophical underpinnings of quantum computing, Scott Aronson has a very nice book, Quantum Computing Since Democritus, which will discuss things like no cloning and other foundational principles of quantum computing.
Thank you.
Thank you very much. And maybe before we now close, I mean, the Q&A, you can say, well, do you think, I mean, we still have a lot of hope, or are we actually overhyped in quantum computing? And maybe Ashley, so what do you think?
Well, I think as a community, we have a lot of both, and like we just need to try to maintain one without having too much of the other. And I think as a very, I would say, generally very rigorous and scientifically minded bunch of people working in this area, I think it's actually easy to go too far in the direction of squashing down the hype and forgetting about the excitement and hope that drove many of us into this field to begin with. So hopefully that's what some of us have tried to convey.
Okay, thanks. And Elham, what about you?
I already mentioned, I mean, like, I have a lot of hope is exactly because of the nature of our field. For me, quantum is not just one topic that is going to, have one-off application and there will be a ChatGPT moment and we just jump out of it. It is just such a fundamental way of revisiting how we're thinking about quantum information that is already affected all of us in terms of re-understanding. So I think if we can manage, the hype is come with the speed of we want to get something. But if you look at how classical computing or even the AI has exploited over the decade, so I think the fact that this field is going through, there is so many breakthroughs of so many brilliant people are coming. Yes, people are picking up the hype as Jens was showing in the article. But if you're looking at the progress of the field over the last decade, it's just mind-blowing. So I'm very hopeful that as long as we can keep the science breakthrough together with the meaningful application and use case delivery, we can manage the both sides.
Okay.
Can I add to this?
Yeah, sure. Jens, your turn.
No. I agree with everything that has been said. I mean, there can also be a bit too much hype. Yeah, sometimes I like to say that quantum computing is exciting even when you restrict yourself to saying things that are true. But I also agree with Elham that there's so much happening these days, and it's moving so fast that we have all reasons to be optimistic, and many of the applications just become manifest as we speak. And now maybe it's the right moment to read my quote on these new applications that we do not know. Here's the quote. The projected device is so radically new that many of its users will become clear only after it has been put into operation. These users, which are not easily predictable now, are likely to be the most important ones. Indeed, they are by definition those which do not recognize at present that are farthest removed from what is now feasible, and they will therefore constitute the most surprising and farthest going extensions of our present sphere of action. Who said it? You have an idea?
Simon.
Yeah, but no, it's John von Neumann in 1945 on
of course, the real computer scientist.
So it was that's the idea to pick up the idea of Ashley showing the old computers. So that's how John von Neumann thought about classical computing in 1945, and we are pretty much in the same regime now, and we talk about quantum computers in the same words as John von Neumann spoke about classical computers in 45. I found that quite astounding.
So thanks a lot, Jens. I mean, also for this insight. I mean, so I hope history repeats itself, and I mean, we will explode with the applications for quantum computing as we did for the classical computing. And maybe Joseph, you might want to add to this. So what's your view?
Well, I think that, for us, some of the difficulty is actually cutting through the hype. And I think, it's such an exciting field. And I mean, we wouldn't be in it if there wouldn't be hope on our side. And I think, especially that close collaboration, between fundamental science and then bringing that fundamental science into applications is super exciting. And I mean, with what Jens said, I mean, I'm very curious, what will be around in 1 to 5 years in terms of algorithms and ideas for applications. And I think, we have to actually work on the use case already now, even though those might not seem promising, to then be ready to actually jump to the really important ones once they appear.
Okay, so thanks a lot, Joseph. Yeah, Hank, you wanted to add?
No, I thought
Okay.
I wanted to close. So,
Yeah, so then, well, let's thank so much our panelists, Ashley Montanaro, Elham Kashefi, Jens Eisert, and Joseph Doetsch for joining us today and also for sharing your knowledge, insights, and expertise. And also thank you to everyone in the audience for your thoughtful and thought-provoking questions, and your engagement truly enriched our discussions here. And of course, a big thank you to also our colleagues at the Institute of Physics and the German Physical Society for organizing and supporting this event today.
Fantastic. So I just want to say thank you as well. I took one thing away. Well, I took many things away, but I like the sentence, stay away from the hype. But I think there's a lot of real opportunity. So thank you. Thank you, Jens. One thing I really would like to impress everybody who attended, we have there as a poll on what the next subject of this webinar should be. So please, if you could fill in this poll, that would be really appreciated. And so, yes, I think, and just summarizing all of that, what I learned today, and I mean, I'm watching on this usually a little bit from the outside. I'm more a quantum sensor person than a computing person, but I am excited about the progress that have been made, the things that have been discovered without yet having this universal quantum computer we can actually use. But yeah, the things we can, I think, already do. Despite not having this, I think this is really, really hopeful and very nice to see. And I think there's a lot of realism in there. Yes, and there's some hype, but I like you said, we need to make sure that people know what is hype. And I think one of the things I find all the time when I say people I'm dealing in quantum, they say, oh, what is a quantum computer? And then they ask me, oh, is this a computer that is working faster? And you kind of say, well, it depends. And I think this is really important that people understand the applications are not all the applications, but they're specific ones. So that's my closing remarks. And thank you again for everybody who participated. Thank you.
Thank you, everyone.
Thank you.
Thank you.
Thank
Bye.
you.
Bye-bye.